first question asks, determine the minimum ratio of carbon dioxide to carbon monoxide that will suppress reaction 2. Why does manipulating the reacting mixture composition as the opportunity to suppress the reaction? If we have a reaction mixture that gives us a Gibbs free energy of this value, it wants to proceed in the reverse direction in order to achieve this minimum Gibbs free energy situation. However, if this reaction was never allowed to take place in the forward direction, it means that one of the reactants is actually missing, and that even though in terms of equilibrium it wants to go in that direction, it's not possible because it doesn't have any calcium sulfide in the system that it can react with. However, if this ratio is such that it is less than our equilibrium constant, which represents this minimum in Gibbs free energy, the reaction will want to proceed in the forward direction in order to achieve this minimum in Gibbs free energy. Since we have calcium sulfate available and we have carbon monoxide, this reaction will take place under those conditions. Therefore, for a reacting mixture that falls in this half of our graph, the reaction would like to proceed in the reverse direction, but it's not possible, and subsequently reaction 2 would be suppressed. Since we are asked to calculate the minimum ratio, that refers to exactly that point where the opposite will start to happen. This means that we have to calculate the exact equilibrium composition, the composition at that point where the reaction will just be suppressed, no reverse reaction will be possible. By applying our equilibrium constant, we can determine that that ratio of carbon dioxide to carbon monoxide in the reactor must always be larger than 1.676. What we must now keep in mind for subsequent calculations is that the mixture composition applies to all three reactions. It is in the same reacting vessel. I cannot have a different mixture composition just because I'm considering a different reaction that occurs in that same vessel. So when we are asked what the maximum mole fraction of SO2 in the reactor will be when reaction 2 is just suppressed, it implies that this reaction mixture, or this is the composition or the ratio of carbon dioxide to carbon monoxide in the reacting vessel. Since we want the maximum mole fraction of SO2, it applies that that reaction reached equilibrium. From our equilibrium composition relationship, we can see the variables that we know. We know the equilibrium constant. The pressure is 1 atmosphere, which is the same as the standard state pressure, so this ratio becomes 1. We know the mole fraction ratio of carbon dioxide to carbon monoxide, and the only unknown in that equation is the mole fraction of sulfur dioxide. Substituting all the known variables in that equation, we can now calculate the mole fraction of SO2 at equilibrium for reaction 1 as 0.185. The last question wants us to check whether this third reaction, where calcium carbonate is formed from some of our reaction products, will actually take place under the equilibrium conditions with the equilibrium mixture composition as experienced in the reactor. If this reaction is at equilibrium, it implies that the 1 over the mole fraction of carbon dioxide must be equal to this pressure equilibrium relationship. However, we want to determine with the actual composition in the reacting mixture, is this ratio larger than or is it smaller than the reaction equilibrium relationship times the pressure divided by the standard state pressure. If it is larger than that ratio, it implies that we are on the right-hand side of this graph and that the reaction wants to go in the reverse direction in order to re-establish equilibrium. If it is smaller than this relationship, it implies that we are on the left-hand side and the reaction will proceed in the forward direction. Since there are no calcium carbonate initially present in the reacting mixture, it implies that when we are on this side of our relationship, no forward or reverse reaction can take place and the reaction will be completely suppressed. Since we know the mole fraction ratio of carbon dioxide to carbon monoxide, we know the amount of SO2, we also know that the sum of all the mole fractions in the vapor phase must add up to 1. We can calculate the amount or the mole fraction of carbon dioxide in our reacting mixture. With the mole fraction that we determined of 0.51 substituted into that relationship, we can determine that the 1 over carbon dioxide is 1.96, which is larger than our equilibrium constant relationship, and this implies that we are in the blue side of our graph and the reaction will be suppressed.